Welcome to our short speech or introduction about the EN 17206 Annex D. End-user information on safety functions. That sounds a little bit like technical. This picture looks as it would be fun, but indeed it is very technical. So we had this speech again some months ago on a different conference in German language, so we decided to do it in English this time, for those of you who really would like to have an English version to follow it. Yeah. So the Annex D of EN 17206, the EN 17206, that is the European standard for machinery that is used for lifting and load bearing in the entertainment industry. And this standard was established or released in the year 2020, so it is effective now in most European countries through the last 3 years. But when we're talking about the authorities who are doing the acceptance testing, we find that still in the end, although there is a lot of details in the standard to be specified, many of this information is still missing. So that's why we decided to talk a little bit about this so-called Annex D, the mandatory end-user information on safety function as specified in the standard. For short, for introducing us, my name is Oliver Brück. I'm the head of marketing and sales from Waagner-Biro Stage Systems. I do this speech in my role mainly as also a member of the technical expert group for the CEN-TC 433. That is the group that is working on the European standard and currently updating the standard. And here with me is my colleague Steve Gergen. He's the head of our customer care program for the CAT system. He will take over some parts of the risk analysis, safety manual, and safety calculations for the safety functions because he was the expert in our company to do that in the past years. So the Annex D, that says the manufacturer shall supply information for the implemented safety functions as applicable. Information shall be displayed prominently on the equipment or in the manuals. And if there is additional information necessary, it shall be also provided to the user, to the end user. And it also says that this information shall be based either on design data or data derived from testing, so from empiric data from acceptance testing. And we should give you the information where this data is taken from. And in the end of the day, it also says that in principle, all this data, this technical information that is provided, shall use combined information about response times of electrical and mechanical systems. So that all sounds a little bit abstract, and you might not know, well, who is actually the target group for this kind of information? Who is this end user that might be interested in this kind of information? So actually, when we developed this Annex D in the standards group, we had a very long discussion about all the additional safety functions, safety measures that were introduced with the new release of the standard. And we found that it is very, very complicated to calculate lots of these things and also to understand what effects will a safety function have when it is applied in the control system or to the machine. So there is a whole group of end users that use our machinery that possibly today even don't know what limitations or what factors they have to deal with. So first of all, it's the set designers that actually need to know the necessary strengths and design factors when they do a set design so that they can understand how the machine could behave or would behave that is carrying the machine or that it's moving the machine around. It's of course the riggers who connect the decoration to the machines because they need to know what they need to use for rigging, what kind of chain, slings, what strengths it should have. It's the machinery operators that need to decide when they're programming their cues, when they're programming their moves, how they shall program it, if they need to use any special safety measures, if they need any special safety modes in the control system, or whether they should reduce for example, the speed or the maximum acceleration for this object that they're moving. At the end of the day, overall, the technical directors of the venues, of course, responsible for all this because every move is creating a temporary machine. And so, as the technical director, you have to be sure that this machine is within the safety regulations. I'm talking about safety functions. Some of you might not know in detail what a safety function is. The definition from the standard says, well, a safety function is a function that is intended to achieve or maintain a safe condition for the machine in respect to a specific hazardous event. So a safety function is nothing that can be seen in general for a control system or in general for an installation of a machine, but it's really specific to a specific machine design and also to the use of this machine. The standard Annex gives an overview of recommended safety functions for typical use cases that we see in the entertainment industry. These are basically listed in Annex C and proposed as recommended or highly recommended safety functions for the typical applications. As an example, you can see here the 6 use cases that are defined for machinery that is used in the upper stage machinery, so power flying machinery from UC1 to UC6. These use cases define what is the intended use or typical hazard that is implied by this machine. So UC1, 3, and 5 are always statically deterministic loads, individual axes that are being moved, and UC2, 4, and 6 are about synchronized motion, where several machines are used for synchronized moving equipment around. UC1 is lifting machines where hardly anyone is in the hazard zone, the typical rigging chain hoist that you would use for setting up a temporary stage, for example. A UC3, UC4 is what we understand is typically the machine we have on a theater stage, so a machine that might be doing scenic motion, it might be moving while people are in the hazard zone. And these people could be the actors, could be technicians doing the setup, but could also be people that just spontaneously cross the stage while you're working there. And UC5 and 6 are the use cases defined for machines that are built for intendedly moving people around. So like a point hoist, a performer flying hoist, or a 3D flying set that you would use for flying people. Of course, all these use cases also exist for understage machinery, so for stage lifts. There is an additional table C2 for lower stage machinery lifting. There is a table C3 for lower stage machinery horizontal. So in principle, the design idea or the idea of the standard is that for any kind of machine and application of the machine, you would, for the typically used design principles, you could find a list of recommended safety functions. And for each of these safety functions, you should, in the end of the day, as a manufacturer, hand over this end-user information table about what this safety function is doing to your machine, is doing a declaration when it applies. In this speech, and this will be very technically detailing how we come to these results and how we calculate everything, we're focusing on, for example, on the safety function protection against improper winding, which is highly recommended for any kind of upper stage machinery in the European standard. We are doing everything of this on basis of a zero fleet winch as it was built in one of our recent projects. That was a flybar hoist in the Festspielhaus in St. Pölten in Austria. A typical UC4 hoist, so synchronized motion, not intended for flying people mainly. And as I said, the safety function is the protection against improper winding. Or in the CAT system that we use for controlling this machine, we identify this safety function as ESWM, safe winding monitoring. Here you can see the machine, how it is installed. So the zero fleet can be used in vertical, but also in horizontal mounting. Here it is vertically mounted. And especially the sensor or detector that we are using for identifying the trip, the safety trip, is a metal plate that is connected, as you can see here. So if the steel cable is winding across the drum or across each other, then you will have an earth contact and shut it down. So this to be have the technical parameters. About the process in this short presentation, I will now hand over to Steve. He will give you an idea or a short overview of how to get from a risk analysis to a safety requirement and how we do the calculation and validation of the safety level that is achieved in our control system. And then I will take over again for talking a little bit about determination of timing, distance, and acceleration. So this is the information that we give to the end user.
Thank you, Oliver. So yes, the first part will be how does it start? Basically, it starts with a risk analysis because we need to say, okay, in this scenario we can have a problem. We need to identify, we need to quantify, is it dangerous, is it coming oftenly, and so on. And then we will need to associate one safety function to this specific risk. And then we will need, during the design process, basically, to quantify and to say, okay, the implementation we've chosen, the components, the architecture, and so on, will meet the different specifications that we had. So, okay. So why risk analysis? Basically on two main points, I would say. The first one will be at the beginning of the project during the design phase, because that's at this very moment when we need to list all the different occasions, hazards that we can meet, all the different scenarios, and this is valid for the whole lifetime during commissioning, during normal use, during maintenance, and so on. So this is the first part. We need to be sure which component, which architecture basically we are going to choose, we are going to implement. Is it meeting really the different situation we are going to meet on site? So this is the first point. The second point will be then information qualification for, let's say, all the more administration stuff like the Appendix D, for example, or all the listing dealing with the CE. So the first step, which is dealing with the risk analysis, let's say there are 5 main steps during the risk analysis. The first one will be basically here a complete list of all the different hazardous situations that the users or all the different people who are working with the control system or implementing the control system and also the electromechanical devices will meet. So basically that's everything that can occur during the montage, the commissioning, the normal use, during maintenances, and so on. So everything, all the different hazards are listed, all the different causes, consequences, and so on. Based on that, basically there is a second part, an intrinsic risk assessment. So basically we are saying, okay, in this case we've got this risk, that's this severity, there is this occurrence probability, this avoidance probability, depending on the scenario we've just identified. Based on that, we have to ask ourselves, okay, is it possible to have some reduction of the risk? In this case, this can be done by organizational measure, like more training, informative, and so on. So this can be really, for example, implemented on the user side or also on the designer side, because during the design process, we have to ask ourselves, basically, can we implement something else or can we do it differently so that we can lower the risk, the intrinsic risk? Based on what we've found, what we've estimated as reduction measure, then we make another risk assessment. So that's basically the second one, and that's the very moment when we are saying, okay, that's, let's say, the definitive configuration, and with this scenario, basically, we'll have to have SEAL 3 or SEAL 2, SEAL 1, only monitoring, and so on. After that, the last step is to say, okay, I've got my whole overview of my site, of my machines. I know that I need to meet the following requirements, SEAL 3, SEAL 2, and so on. And I need to say, okay, the control system then needs to provide this kind of safety functions. Short detail how the different risk assessments are done. Basically, it's, let's say, quite straightforward. Everything is quite explicit in the standard, the 17206. Basically, on the left side, you can see there is the severity with the different consequences. So, of course, for one scenario, we say, okay, in the worst case, we can have this consequence. So basically, that's the left part of the table. And the right part of the table, that's the different, let's say, probability that we can have that this phenomenon will occur. So this is dealing with the frequency of exposure, the probability of that the event is coming, and the avoidance probability. And based on the estimate, the situation, the scenario we've identified, basically we use the different numbers and the different grading in order to determine if a safety function that should meet SEAL 3 or SEAL 2 or SEAL 1 must be implemented in order to cover the different risk or the different situation that we've identified at first in the risk analysis. So basically, we've made, let's say, the first step. We've said, okay, we've got different risks, and we need to have different safety functions. Now we come to the second part when we say, okay, we have to find the components, the architecture, and so on, and we have to be sure that basically the way we want to implement it and the way we are using it is meeting the needed requirements. So at start, we take at first step the result of what we had just a little bit before. So basically the result of the risk analysis saying I need a safety function for this specific scenario, which is minimum SIL 2 or, for example, SIL 3. Based on that, we are going then to write requirement specification. So this means for each safety function, we need to make a description, what really the function is doing. We need to then begin to specify the different diagnoses. Are we checking a sensor? How we are checking this one? The operating modes. This means, is this safety function only valid during normal use or also during maintenance? For example, when you've got some work like a change of the encoder and so on, when you've got the safety function which is encoder monitoring, during normal use or during maintenance, it's completely different because the purpose and the use of the different sensors are different. Then we have also to identify the priority and possible conflicting action between the different safety functions, because of course we want that our system to be safe, and so we want that we avoid any kind of emerging behavior. And then two last specification, basically the error reaction, how the system should react. So this means, do I need to really directly cut the power, close the brake, or am I just performing, let's say, another slower ramp with a safe operating stop and so on. And then finally, let's say a response time that we need to specify and that we need to qualify after the commissioning when we are doing let's say, the stress test of the different equipments. So basically, to make the qualification of a safety function, there are, let's say, several points that are taken into account. Basically, that's the left part. The first one is the architecture. Okay, basically, I've got a concept for my safety function. So this is more dealing with the mechanical and electrical implementation. Do we have, for example, two encoders separated, one on the drum hoist, or for example, the other one on the motor, the axle, for example? Then we've got a second point, the control system itself. On the previous step, we said, okay, I need to make this diagnose and so on. So here, all the interface monitoring, all the different tests that the control system is performing on the different sensors needs to take into account. Of course, the components, because architecture is one thing, but the components, let's say that's the second leg, I would say. Because we've got for each component a failure rate, and we need to identify that when we've got everything concepted, everything implemented, that the whole chain is basically meeting the requirements. And then, of course, as let's say last point, that's the stage machinery use. So basically we have to estimate, okay, this problem, this hazard, this issue can come 10 times a year, 5 times a year, or can be more. Like this. Also, the frequency of the use of the machinery is important, because if you make the calculation for a machine which is moved 5 times a year or 20,000 times a year, you've got, of course, different results, and perhaps you have to choose different components based on the failure rate and the results of the calculations. And then the process is basically, we are building a block diagram, I will show a little bit later, when we try to identify and simplify the situation, so we are able to quantify each part of the system. And to qualify the safety function, we do it with two different ways. The first one is basically the justification of the failure rate, so let's say that's really an Excel calculation. And the second one is more the justification against architecture. Okay, if you take the example we have, like with the improper winding monitoring, what we have in this case is we consider to implement as follow. We've got, for example, here one drum, and here we've got one isolated bar. That's our sensor. Our sensor is basically interfaced with our axis controller, here electrically, and our axis controller is then performing some tests. I will speak about this a little bit later. And here on the left, I'm still drawing something like, okay, I've got also encoders, frequency converters, brakes. Why? Because when we say we have to quantify that the improper winding monitoring is safe, we need to estimate not only the sensor itself, but the whole safety chain. So this means, okay, my sensor is detecting an issue, but I need to stop safely my drive. So that's why I need to take into account the encoders, because I'm doing a braking ramp, also the frequency converter, the brakes, and so on. So that's why all these parts appear there, even if on the first thought, I would say we would have only considered, let's say, just the drum, the isolated bar, and the axis controller. But this is very important to check really that the overall electromechanical plus control system, the overall is matching the standard. So what we are doing is basically we are doing simple block diagram saying, okay, I've got a subsystem that's the winding sensing. So here, I've got another subsystem which is basically my axis controller. I've got another subsystem saying, okay, I've got my sensors for the positioning and the stop of the drive. And then I've got my frequency converter and my brakes. Basically, then we are saying, because that's very important for the calculation of the safety function, okay, my axis controller will make different checks. It will make a permanent checks, or it will make dynamic diagnose, like stuck at 0 volts, stuck at 24 volts. I've got some tests like pulses and so on. I'm checking this every maintenance, and based on all these tests and all these, let's say, diagnosed properties, I can then later use the correct data to make my calculation and to estimate if I'm correctly meeting the requirement. And then the third point will be basically the reaction. Okay, what happens when I detect, for example, an improper winding? In our case, we make a safe stop emergency. So in this case, the converter is stopping the drive. We are not stopping brutally with the brakes, but with the converter, and then we make this safe operating stop, and then we close the brake, because we don't want to stress the machine more than it should in this specific case. Of course, in other case it can be that really the power cut is needed, but for this case, in the improper winding, we want to make the thing a little bit more smoothly, basically. And as mentioned, in case of a failure, because the axis controller is monitoring what happens when there is detection, we stop with a dedicated ramp, we set to the converter. If there is a position deviation, then we close the brake, we go, let's say, the hard way, we cut the power, and we do it brutally. So basically, to make the calculation, we need for each component a couple of information, and this information can be found on certificates, on data sheets, and so on. So here is, let's say, some small list of what kind of component we can use. Basically, they are known as B10, B10D, MTTF, and so on, or failure rate. So everything there can be just found on data sheets or the different certification we've got from component. And for the calculation, the second part important is the machinery use. As said a little bit before, it makes quite a difference if we say that this drive or this system will be moved 5 times a year or 20,000 times a year. And now to go through the calculation, what we are doing is basically, we've said, okay, we've got different subsystems, one for the winding monitoring, one which is the axis controller, one for the encoder, one for the motor and brake. And basically we are, let's say, breaking down a little bit with some additional blocks. And based on that, we'll be able to estimate and make the calculation of each blocks. And at the end, we are gathering the overall. So basically, once we've made the let's say the breakdown structure of the different blocks and safety subsystem, we are doing the calculation of the different failure rates, which is, basically here the calculation on the middle. So based on different parameters, the different parameters, like also the diagnosed coverage, which is depending on what my control system can do. Is it just doing a monitoring? Is it doing some specific test? Is it doing some cross-checking between 2 or 3 sensors and so on? Again, the test and diagnose made by the control system has, of course, an influence on the calculation. And then, based on that, once I've got the different failure rates of the different subparts, we bring everything together, and then we can say, for example, for each of the first blocks we've identified, okay, for example, for only the block winding monitoring, then I've got, for example, this result, so this failure rate, and in this case there is a standard table, basically in the standard 61,508, which says, okay, if you've got this failure rate, then you're seal 2, this failure rate, you're at seal 3, and so on. Then we need to, so that was the first part, justification by calculation, breakdown, and then we calculate each small part, and then we bring everything together. And then we need to make the second step of the qualification. So basically, that's the justification through architecture. And in this case, it's more depending on the architecture itself. It's like, do I have only one channel, or do I have two channels, and so on. And also, depending on one of the results I had during the calculation, I can say, okay, I've got a certain proportion of safe failure fraction, which means, okay, my subsystem can have safe failure. So this means I can have a problem with one of my components, but for example, it's not dangerous. Or I have a certain part that I can have an issue with my component, but in this case, it's dangerous. Like easily a contactor can be, depending on the case. If my contactor is completely stuck open, perhaps it's not dangerous at all. But if, for example, it can be stuck, let's say completely closed, the current can go through. And in this case, that's, for example, a dangerous failure. And then after that, basically, we cross-check everything. We just make the parallel between the architecture justification and the calculation justification. And based on that, we are then saying, okay, we are meeting, for example, seal 3 or seal 2. So again, based on calculation and the architecture itself.
Good, thank you, Steve. So far we have understood what the machine is going to do. We have defined a safety design. We have calculated and verified that we reach a certain safety level. So now we know that with whatever components or design we go into the calculation of the effects of this safety function being applied, we can then calculate how the machine will behave. So what will be the resulting timing, distances, and acceleration that apply to the decoration or to the performer if the safety function is applied. So first of all, in our example, the protection against improper winding, as Steve already said, we can apply, we usually in a CAD system, we would apply a category 2 stop, or I could also choose to have a category 1 stop. So I do a controlled deceleration with a set deceleration rate, and that deceleration rate is determined and defined by the mechanical design engineer. So the mechanical design engineer says, I want to have, in this case, for this winch, 8 meters per second square deceleration rate as an emergency stop rate. And regardless of what will happen, regardless of the load case, if it's going with full speed, if it's going with a lower speed, if it is fully loaded on an empty bar, it will always apply this category 1 stop, 8 meters per second square, resulting in a worst case reaction time. That is the time in between the trip is identified. Maybe there's some filter time to eliminate false positive trips. There is a reaction time in the control system for processing the error input, maybe also for doing some synchronization between several axes on the system. So here we say the worst case reaction time we would have for this kind of error would be 0.112 seconds, so 112 milliseconds. And the worst case travel distance we would go in this time would be 224 millimeters. That is basically a very basic I would say mechanical calculation. You see here on the diagram, you have on the one hand the speed, the maximum speed the hoist can go is 1.2 meters per second. I have the reaction time of 112 milliseconds and the given deceleration rate, and with that values I can, in this configuration of a safe stop 1 or safe stop 2, predictably calculate and define the stopping distance, which is 224 millimeter, so like a little bit more than 20 centimeters. So for any kind of errors or safety functions that use a safe stop 1 or safe stop 2 as the reaction to the safety trip, this distance would be similar. It might be that the reaction time is a little bit different because there's more synchronization. It might be that the reaction time is a little bit longer because the sensor has a longer reaction time. But in principle, all the values would be in a very similar range. Something totally different is in case of a category 0 stop. Because on the category 0 stop, we do not use the drive for controlled stopping of the machine. But the category 0 stop says we have no power or the drive is broken itself. So we have a torqueless drive, a torqueless motor rotating, and we have to stop the machine by the brakes only. And as you can see from that list here, we have to consider different scenarios in this case. So the fastest deceleration rate that could appear is if you have an empty load, if an empty bar with no load on it, and all safety devices or load securing devices, so all brakes are operating together, and all brakes have the maximum torque they have. So normally you specify a certain brake with a certain torque, but it has tolerances up to plus 60%. So under this worst case, or under this consideration, maximum torque tolerance, no load on the machine, and both brakes acting at the same time, you could have a resulting deceleration of 24.2 meter per second square. The other way around, if your bar is empty, is fully loaded, and only one of your load secure device, only one of your brakes is operating with its minimum torque, you would result in the slowest deceleration rate of 4 meter per second or 4.3 meter per second square. So you can see that there is a huge difference in between the possible effect when you're doing a category 0 stop, just talking with the brakes. The reaction time that you see here in this case is then it's not taking into consideration any processing in the control system anymore. It's really the time it takes for the rectifier to unload, for the contactor to close, and for the brake coil to close the brake actually. The resulting stopping distances would then be something between 18 centimeters and 40 centimeters roughly. So see that there still is a factor 2 in the resulting braking distance in a category 0 stop. So something totally different from the predictability we have on a category 1 or 0 stop. So if we calculate then the resulting deceleration rates at max load, we always have to do this at max load and min load. You see that there is an effect. If the category stop event is happening, there's a reaction time. So in this time, there's no torque on the motor, and the machine starts decelerating. And the deceleration is not fully with gravity, because there's, of course, the inertia mass of the motor that needs to be taken into account. But you see that you still have a certain time, reaction time. In this time, the motor is even speeding up. And then you have the given the brakes apply, and you have a given stopping time. So depending on the brake torque that you have in this consideration, you would have something between 4.35 and 9 meter per second square deceleration time. Deceleration at maximum load. With minimum load, same again. Speed is the same, reaction time is the same, the acceleration is the same. But of course now with minimum load I have the maximum deceleration applied. So the deceleration, depending on the braking torque, can be something between 9.24 and 15.25 meter per second square. If you well remember, a few slides before, I showed a maximum deceleration of 24. So that is different from the 15 that you can see here. And there's one good reason for that, because this diagram and this way of calculation is considering a rigid body system. So everything is connected rigidly together. There's no spring effects and nothing in it. But of course, with the winch drive, we do have a wire rope. And the steel wire rope has the effect that it has some tensioning depending on the load that is lifted on it. So during the acceleration phase, the load on the rope accelerates both the load and the rotating masses, as I said. So the acceleration is less than the acceleration due to gravity. And during the deceleration phase, of course, the braking torque is applied, and only the part of the braking torque that is higher than the then the acceleration is stopping the rotating masses and the load afterwards. So with this, what I said, rope elongations at maximum load, typically if you take a rope length of typically 20 meter in this configuration, normally during the max speed, the rope elongation would be 27 millimeters. But if you're going into this acceleration phase after the event, when the motor is no longer under torque from the drive, this the elongation on the rope will be a little less, so it will be only 17 millimeters. And then when the brakes apply, there's more torque on the rotating part of the machine, then the rope will be stretched again, and so the rope elongation will even be more, up to 50 millimeters if the maximum braking torque is applied, or 38 if the minimum braking torque is applied. So see that in this consideration, also the elongation of the rope is almost a double. If you take this into account now when calculating the resulting forces, you can see that, well, in the rigid body system, we had the 27 millimeters. Here we have something in between 17 and 50 millimeters. So if you can either simulate it, and you see in the elastic system you have then, once the event is happening, so in the acceleration phase, this takes a little bit longer to release the rope, and when the brakes apply, when the braking torque applies, the whole acceleration of the load of the bar itself overshoots the values in the rigid system, or even by a factor 2. So you can simulate these kind of things with suitable programs. That's what we've done in the past in several studies, and also taking empiric checks of it for evaluating if it's right. But you can also, which is quite good, is coming quite close, take calculation help specified in the hoisting standard EN 13001-2. There it's a factor phi5 that is covering this acceleration peak. And in this standard, it is given, or there's some suggestions for factors for the acceleration peaks that are usable in the stage machinery hoists as well. So this is typically between 1.5 and phi5 being 2.0. And with these parameters, you see that in the max load scenario, you would have a deceleration something between 16.1 and 24.8 meter per second. And in the min load configuration, same factors applied again. You would have something between 24 and, worst case, 33.4 meter per second square deceleration rate. In our table, we specified this 24.2. Why? Because from our experience, also the studies we've seen, we've mentioned that, of course, the brake torque does not apply immediately. So if you simulate it correctly with an increasing braking torque where the brakes are closing, then the simulation comes to this level, which is 24.2 in this consideration. That is then the value that we would specify in the end user table. So resulting, you can see that on a category 0 stop, the resulting effect on deceleration is massively higher, or can be massively higher than for a category 1 or category 2 stop. Although the stopping distances are not so much different and not so having a big impact, this acceleration, deceleration is something that the rigger, that the set designer definitely has to take into account. So if I can summarize this is now a lot of theoretical information about safety design, electric design, mechanical design in the end of the day, something that you as an user, as a rigger, as an operator of a stage machine would typically not want to calculate or evaluate during your daily work. So if you get a set piece to rig or have a person to fly on your machine, you would like to have a table that gives you an overview of all these resulting values, and that really is the idea behind this Appendix D documentation. So for this machine that we've used, for example, the resulting table, Annex D table in the project looks like this. It defines, for example, the category 0 stop, as I said, 24.2 meter per second square as the fastest deceleration rate possible. It defines all the individual values also for all the other safety functions like the emergency stop, stop on hold, protection against position deviation, speed deviation, and all the other safety functions that are defined for this machine. So in total we have 15 to 16 different safety functions that we use for the risk mitigation on this machine, with all giving with the resulting values, worst case travel distance, that you need to consider when dealing with group synchronization, and yeah, of course also the forces that your set or your person has to withstand. What you need to understand if you get this table, that, as I said, this table is individual for each machine in your installation, that you still have to read and interpret it in a way to understand what this means, what you're going to do with this information. As I said, in a control system like the CAT V5 system, we use mostly category 1 stop and category 2 stop in the safety systems or in safety functions, just because the reason that the emergency deceleration rate is predictable, it is shorter, and it's more harmonized for the operator. So the category 0 stop can still happen. So we cannot say that you do never need to take this into account, but the possibility of this failure happening is rather low compared to the kind of safety functions of failures that you have on your daily operation. For example, like a slack rope, overload scenario, this kind of things that just happen from using the machine in their intended use. So there is one thing, this is the worst case deceleration that rarely happens to the persons or decoration parts. But on the other hand, you can get a quick overview, a very good overview for this machine. Well, what is the predominant effect of a safety functions for the decoration or person? So if you go through the list and you see all of them, most of them are category 1 stop, category 2 stop, and all have a very similar, what I say, deceleration rate and very similar resulting stopping distances from that, you can quickly understand and define how you have to rig your decorations, how you have to connect a large ceiling, for example, to a group of flybars. Yeah. And you can, of course, if you're working with persons in the danger zone, very quickly understand whether from the design intent of the manufacturer of the machine, it is permissible to have persons in the danger zone during motion by identifying which safety levels or which SIL levels are actually achieved with the design of the system. So as a summary, the Annex D describes not only which safety functions are implemented for each machine that you have, but it gives you also an information about the quality of the design, of the safety design of the machine, and the impact on the everyday stage operation. Thank you. Do you have any questions? So if there are no questions, or if there are any individual questions later on, please come to our booth. We're both there the next days, booth E32 here in the hall. Thanks for your attention, and hope to see you soon again.